Alright, let us take a look at an example of a Covnet now. And that Covnet is inspired by LeNet 5, and you know that Jan LeCun pioneered Covnet and developed the first popular Covnet at the end of the 80s. Yeah, remember that he used the net to write, to recognize digits. Yeah, and that technology was used by the US Postal Service to read handwritten digits on envelopes for zip codes. Yeah. So basically what we have is we have a digital number here, or a digit, and the size of that digit is 32 by 32 pixels. Yeah, and it will have 3 channels. So theoretically or practically this means a color image digit. So the number of, so the activation shape gives a total number of pixels is 32 times 32 times 3, and the 3 is for RGB. So that means the size is 3072. Yeah, if you calculate this one, it's 372, and there's no parameters. Another thing we know is that the pooling layers also don't have any parameters. Here we go. So we can put 0 there. So what is the outcome here when we take a filter of size 5 with a stride of 1? Well, remember, the formula is n minus f plus 1. N is 32, f is 5. 32 minus 5 is 27, plus 1 is 28. Yeah? So the height and the width go from 32 to 28. In terms of number of filters, we're going to use 8 filters. Yeah. So here conv1 is 28 times 28. Yeah. Times 8, because we're going to use 8 filters. So the size will be 28 times 28 times 8, 6272. Okay. The number of parameters, well, the parameters come from your filter. So your filter here is a block of height and width 5, and depth is gonna be 3. Yeah, because the depth of this one and the filter needs to be the same. So you calculate this, 5 times 5 is 25, times 3 is 75, plus 1 for the bias is 76, and we have 8 of them. So the number of parameters is 8 times 76 is 608. Okay, so then we have a pooling layer where we use, you know, a 2 by 2 window. So we have stride of 2 and a filter of 2. There's no parameters, as we know, but we know that the size is going to be divided by 2, as we've seen in the previous video. So you will have 14 here, 14 here, and you will still have 8 filters here. Yeah. So this pooling is 14 times 14 times 8, and that is 14 times 14 times 8, 1568. 1568. Alright, so now we're at the second convolutional layer. And so what is the size? Well, it's n is 14. Yeah, is 14. F remains the same. So that becomes 10. Yeah. 14 minus 5 plus 1, that becomes 10. So height and width is 10. 10, and the number of channels we're gonna double now. We're gonna take 16 channels. Yeah. So conv2 is 10 times 10 times 16. Yeah. So it's 1600, right? 1600. And the number of parameters. The number of parameters is is 76 again, because again it's 5 times 5 times 3 plus 1 is 76, but now we have 16 filters, so it's 76 times 16. 76 times 16 is 1216. 1216 parameters. And then again we have a pooling layer. Remember, pooling layer, we're gonna divide the size times 2. So this is gonna be 5, and this is gonna be 5, and we're still gonna have 16 filters. So it's 5 times 5 times 16. So that's 25 times 16. That's 400. Yeah. And no parameters for pooling. And then of course we're gonna end the convolution process, and we're gonna go to fully connected layers. I have two fully connected layers here, FC1, FC2. But before we can do that, we need to flatten that picture. Now we can't keep it as a square. We need to flatten it and make sure all the digits come next to each other. Yeah, so you're gonna have a huge vector of output size 400. Yeah, you're gonna have 400 rows here. So 400. The length of this flattened vector is gonna be 400. Yeah. All right. So for fully connected layer 1, we're gonna take 120 items, yeah, and the second one we're gonna take 84. So what is the activation shape here? Well, it's gonna be 400 times 120. And 400 times 120 is 48,000. And this is of course 120. Also 120. Yeah. So in the next one, so this 120 and one column, yeah, so times 1. And the next one we have an 84 fully collected layer, so that's going to be 84 times 1, and that's 84, yeah. And the number of parameters is going to be 84 times 120. 84 times 120, 10,080. 10,080. All right. And then at the end we have a softmax layer with 10 potential classes, meaning the digits 0 to 9. So you have here a 10 by 1. Yeah, is 10. And the number of parameters is 10 times 84 is 840. But here I need to add one for bias. Yeah, something I forgot. We need to add one for bias in this tree. Yeah. So here we are at the end. Now if you count the number of parameters, you see that you're going to have roughly about 60,000 parameters. And we mentioned that in another video that Jan LeCun used 60,000 parameters. A few things that we see is that, well, first of all, the size of the image shrinks, and we know that. We know that, that's not a surprise. But something else that we see is that the number of filters actually increases as we go along. Another thing that is interesting to notice is that look at the number of parameters of your convolutional layers versus the number of parameters of your fully connected layers. So these are 60,000 parameters, but 58,000 is linked to the fully connected layers. Yeah, these two layers here. So that shows that convolution is much more efficient because of the sharing of parameters. Alright, one more thing about Covnets, yeah, and let me take this off here. You will hear the term translation equivariance or translation invariant. Yeah. Basically, the true term is translation equivariance. That means that here you have two images of a 9, but the 9 is in different positions. If you convolve this with a filter, you have the same output here, but displaced with the same displacement as here. So I don't know what the output gonna be. Maybe it is gonna be something like this. Yeah. Well, in the second image, it's gonna be exactly the same, but at the position where the 9 is here. Yeah. So that means equivariance. And then there is another little secret I need to mention is that pure technically what we're doing is not convolution, and we call it cross correlation. Why aren't we doing convolution? Well, remember, in convolution we had this sum where we multiplied xk with the impulse response n minus k. Yeah. And so when we did our convolution and we developed our filter, remember the example, we had an h like this. Yeah. We saw a convolution example. So this was our h. The first thing we needed to do is we needed to flip it. Yeah. So we flipped it. And then we used this filter. Yeah. This is something we don't do in convolution. Yeah. So pure theoretically, it's not really convolution happening. Yeah. But it has no impact on the result when it comes to machine learning. I just want to mention it because you may encounter this topic as well. All right, let's now start to write our first code, and